Hi, GM. I'm Samarth, and in this video we're going to be discussing real-time blockchain endpoints. We'll be talking about three chains: MegaETH, RISE and Abstract. So if you're active in any of these ecosystems, you've probably already heard of it. So let me start by giving you a little background. The scenario in 2025 is that chains are focusing on speed and latency. So they're optimizing for blazing fast performance. And by blazing fast, I mean sub-millisecond performance. So MegaETH has a special feature called mini blocks, which are mined in around 10 milliseconds. Similarly, RISE has shreds, and these are mined in about 5 milliseconds. These mini blocks and shreds are canonical, which means that they will definitely be included in the full blocks of their respective chains. Now, with chains becoming as fast as Web2, there is a change that we can do on our client side to make the experience feel more like a simple API call. So currently what we do when we send a transaction is that we just get back the transaction hash. Once that is received, we keep polling the blockchain, which in this case means asking the blockchain repeatedly if it has generated a receipt for a transaction. Let's say you ask the blockchain for a receipt every 100 milliseconds. However, the receipt is generated in 201 milliseconds. So what happens is that you first call it at 100 milliseconds, then at 200 milliseconds, and 1 millisecond after your call, the execution is completed and the receipt is generated. However, you haven't asked for the receipt for the third time yet. So 99 milliseconds get wasted, and at the 300th millisecond, you ask for the receipt again and then you get it back. So you basically end up waiting for 100 milliseconds after your second call when you actually had to wait for just 1 millisecond more. This is the main reason why real-time endpoints, or more technically speaking, custom RPC methods, have been added to these fast chains. So this is what happens in regular chains, and this is how MegaETH and RISE tackle this situation. I'll discuss Abstract later because I have some not so nice thoughts about it. But yeah, in case of MegaETH and RISE, what happens is that our transaction goes to the sequencer, and that generates an execution pre-confirmation receipt, which is essentially a guarantee that your transaction was successful and it will be put on chain. And this receipt is what we were looking for in the first place. It gets instantly sent to us as soon as it is generated, thus saving us time and minimizing latency. MegaETH's special RPC endpoint is called Realtime_send raw transaction, and RISE's endpoint is called ETH_send raw transaction sync. And the RISE team has also submitted a proposal on ETH research to make ETH_send raw transaction sync a standard. I'm looking forward to see where it goes, and I'll also link it in the description so you can check it out yourself. Now, Abstract does it a bit differently, and not to overreact, but I think they're doing it just for the marketing play. In my opinion, they just wanted to join the hype without actually taking the same route. It was like they said, hey, we're going to add a real-time endpoint. So people were like, okay, but do you have the tech? And they said, kinda, and just went on with it. So their real-time method, which is ZKS_send raw transaction with detailed output, does not actually return a receipt. It's like an ETH_send raw transaction, but you get some extra data from it. So instead of just getting back the transaction hash, you also get storage logs and events. It is essentially like doing an ETH send raw transaction followed by an ETH call. Your transaction doesn't even have to reach the sequencer. As a result of that, this approach falls completely apart when two transactions try to modify the same state at the same time. One of them is definitely going to revert. I'm a fan of Abstract myself because they have good tech, plus they've done a lot of work on the consumer crypto side. But this ain't it, chief. Anyway, I prepared a demo to test out all these endpoints, and you can try it out yourself at this link, which I'll also put in the description. So in my environment variables, I'm using the private key of a burner account, and I'm never going to put any mainnet funds in this. You're never ever supposed to put your private key in an env file. The only reason I'm doing it is because this is a burner account, and I know for sure that this will never have any mainnet funds. The reason why I did this is because I'm pre-signing transactions so that we can measure only the time taken to submit a transaction and get back a receipt. If we were to sign transactions on the fly, it would add additional time, and we don't want that. The ideal way of doing this is to actually use a wallet provider like Privy, Alchemy, etc. instead of a local account like I'm doing here. In fact, I've taken the Privy embedded wallet approach in my project Blaze Arcade. Blaze Arcade is a minigame platform for testing the latency of superfast EVM chains such as the three in the video. It is currently in beta, and you can DM me to get access to it. So now let's get to the demo. I'll select a network. Let's go with MegaETH, and it pre-signs transactions for MegaETH. It is actually pre-signing 10 transactions. Once you're through with 5 transactions, it pre-signs 10 more. So after every 5 transactions, 10 more are added to the pool of pre-signed transactions. So now let's test MegaETH. And yeah, it gives us the transaction hash. If you click on it, it'll take us to Mega Explorer. Let's go back, and there's a table that is made below. So now let's test it again. Yeah, transactions are added to the table. Now let's test RISE. So it pre-signs again, and now I'll click test RISE. Yeah, the time is given over here. This will take us to RISE's Explorer, like so. And this is now shown in the table as well. So now let's switch to Abstract. Pre-signs again. Now let's test it. Yeah, this again gives us the transaction hash, and this will take us to Abstract Explorer. Let's click on it. So it gives us the information, and it's also shown in the table over here. So the contract addresses are given over here. Let's switch to a different network. See, the contract is different. Similarly for MegaETH. And yeah, all this code is open source, and I'll link the GitHub repo in the description. So you can clone it, use a different burner account, make sure it's a burner, and experiment with the project yourself. So the whole thing is in page.tsx, pre-signing logic, initialize network, and extend pool. Contact addresses are given over here. And above that, I've mentioned that this is the burner account's private key, and you should never put your private key in an env file. Checking the code is completely optional, of course, and the link to this demo is in the description. So if any of these balances become 0, just copy this address and click on it. It'll take you to the respective faucet. So yeah, that's it for this video. Thank you so much for watching. If you have any doubts, any clarifications, or any suggestions, please feel free to comment down below. Thank you so much.